Record. Okay, so recording is on. And we'll today go briefly through some topics last week. I wasn't quite happy with the material, so I'm still recycling last year's material, but this time I spent a bit more time on remembering what was what. And basically, everything you need to complete the exercises should be on this lecture. So, chain rule, which you should be familiar with, as well as then some trigonometric integration, which we will need in the at least in the final exercise. There are already several ways of doing these exercises, so some of those actually could be just geometric, but well, we'll see in the end of the lecture. Right, hiya. I'll still try to present some stuff on that board, so kindly make sure you pick a seat where you can see what's happening on that board. No, I don't like it. Let's put some more lights. And that's still mostly visible, so. All the clocks traditionally all in different times. Well, roughly about time, so let's start. And we'll, okay, so there we go. So we'll start with a short rehearsal of last week's topics and then go on to chain rule and trigonometric functions today. By the way, if I'm using an odd accent on some, feel free to correct me. So I should speak more English with actual native speakers to develop on that field. I'm going downhill pretty fast on the last few years. But yeah, vectors. So we have two equivalent ways of displaying those. So the component form. So V equals V1I times V2J times V3K. And this is the way we usually mark components. So if you have vector V, so the V and a line on it or an arrow on it if I were really proper, then V1, V2, and V3 are the components for the first, second, and third basis vector direction. And then we could have a length and direction pair. So depends on the application, which is the actual angle. I was using theta here. And then of course we could also define a vector from point to point. And here, it does matter which direction, so it's a good manners to put the arrow on top of that. But that's more or less equal of the component form, because if you have two, for example, three-dimensional points that are shown as triplets, then if you subtract those component-wise, you end up having the component form V1, V2, and V3. And of course, in several cases, we want to also include the information on the location of vector. For example, if we have a force vector, then where exactly we are putting that force. So, but that's formally not part of vector. So vector could be theoretically anywhere in the coordinate space, unless we fix the location as well. Adding vectors, so yeah, component-wise, it's relatively simple. You just add up the components, and geometrically you could then draw so that where one vector ends, another vector starts, and so on. Order doesn't matter because operations are commutative. So you can swap the order of the addition operation, and it, at least in most common arithmetics, it doesn't change the end result. Now, I don't think we are having need for, well, you will have matrix calculations, and with matrix calculations, multiplication is not commutative, but we'll talk about those later. But that's for when you first encounter an operation that you cannot swap the sides, then that maybe is slightly confusing at first. Yeah, multiplying vector by scalar, so multiply length if you have the length and direction, or multiply all components if you have the component-wise part. And if you multiply with a negative number, then it points the opposite direction. So similarly, subtracting vectors is essentially we multiply the vector to be subtracted by -1 and then add up vectors. Yeah, dot product. So yeah, we multiply vector to vector, and it then result is scalar. And the interpretation of this was a projection. So we project U towards the direction of B, multiplied by the length of B, and that's it. So practical component-wise, just multiply components and add up everything. Or if we use the length, so this absolute value means length in the context of or magnitude if we're proper in context of vectors. Occasionally, you also see double bars. So those are called a norm, which, well, the second norm is just the Pythagorean theorem type rule. So it's essentially the length in the Cartesian coordinates. So that's slightly superfluous here. And then the cosine theta is the cosine of the angle. So from that, we can already see that it is kind of a projection here. Basically from the definition of the cosine. Cross product, we multiply a vector with a vector, and we produce something that is a vector itself. So it is the area of a parallelogram, or in Finnish we call it suunnikas. So I want to draw that. I'm gonna flip over to stop screen sharing. Hello, we told them Mike. What was the geometrical interpretation? So if we have two vectors, then okay, these are two close to right angle to display what I was meaning to do. So it's the area here. So essentially this will be the magnitude of U cross B. Here's the area. If this is U and this is V, and then it will point to that, well, that length, somewhere here, U cross B. So pointing on the normal direction. And one application we had on the demos, which I want to maybe do in a bit more proper way, is showing that that is useful for normals. And we had the FBI rule. Actually, that's something I hadn't learned before, because it turns out that our old maths teachers in Finnish high school weren't too interested of FBI. But yeah, the force is here the end result of the cross product, and then, okay, magnetic field and current. So this is one way to remember. So we have the first, so my index finger is the first component, middle finger is the second component, and then the thumb shows which direction the normal goes. So now here, also this is not entirely commutative here, because if you swap the order of the components around, the cross product will actually point into a different direction. And you have probably learned this in physics as having right-angled cases always, which is an easy one. You don't need to know that those are vectors, but now when we're having a cross product, it works on whatever directions we're interested of, except if it's the same direction, because then we do not have a normal direction defined. So usually two vectors, so you could think that you put up two sticks, and you can then put a level plate on them. So two vectors do define a plane, but if those two vectors are the same, then we do not know which way the plane points, and the math breaks down. And we had this determinant that you probably hadn't heard before. Have someone done matrix? Okay, one person. Two. Okay, not bad. So it is actually shows a little bit how to calculate determinants later on. So if we have larger determinants, we can then break them down by components and calculate by that. So to get the multiply of the first component I here, we take the second and third rows of the coefficients. For j, we take which is second, we take the first and third, and for k, which is third component, we take the first and second. And then we calculate the smaller determinant, and the 2 by 2 determinant is calculated such that we multiply those crosswise. So when we have matrix A, B, C, D, and take the determinant of it, we multiply T's and multiply T's, and that one's minus, which was the same rule that we had for the direct multiplication of the 3 by 3 determinant last time. And then I actually checked what Wikipedia does have to say about cross products. It has one more formula. We don't usually use it because this formula assumes we know the normal direction already. But if you know the normal direction, then we do have a definition of multiply the lengths of the component vectors and multiply that by sine theta, which is the angle between those vectors, and that scalar points in the direction of the normal. So that's essentially a different way of saying that the same thing I draw there. So the magnitude of the cross product is essentially the area delimited by that parallelogram. So sine, if you think about the unit circle, I'll actually stop sharing the screen so it's probably then visible on the recording as well. So if we're using the unit circle and theta is here, then the sine theta is this height. So when we're having a parallelogram where the angle here is theta, then sine theta is the height. And what we're doing is, or sine theta times b is the height, of course. And if there's u, then the area of this parallelogram is here. So the area is u times b times sine theta. So that goes back to the definition that way. And this, I'm not sure if you've run into this beforehand, but it's kind of a, well, these days we would say meme or trope in mathematics to have something left as an exercise to the reader. Occasionally, these things are things that the lecturer hasn't been able to do, but in this case, this is actually should be relatively simple, and we have already a definition for it if we use the different way to calculate the cross product. Okay, a little recap on functions and limits. Yeah, this actually we had the last time. So apparently there are a few slides I had taken from this week's lecture for some other course, and then I noted, hey, there's a good package of information on that course, so let's reuse it here. Okay, it still has typo. I corrected the one on the second row, but yeah, x is roughly 1. So then we have this limit. This is now slightly cleaned up, so it's easier to read. This is exactly the same thing we had last week. So if it's continuous on both sides, we can just submit the value of a function, but we need to check that it's continuous on both sides. Fractions, we can do basic maths, so factor and cancel common factors to find something that has a value. Okay, this is a different example, but with the a, we could simplify things, get a value, and then take a conjugate. Infinity, same thing again. Tangents and normals. So the k here is, if we fit this to some function, then the k is the derivative, which is the slope of this tangent, and normal is essentially the normal has the inverse of the tangent as the slope. And then let's go on forward. Any questions at this point? Okay, no, let's go on. Chain rule. So actually, there's a lot of stuff that I personally learned to look from the tables. But how to calculate those things, that's where the chain rule can come to the mind. So if we want to calculate general powers of function, what's the derivative of a general power of function and so on, we'll need to use the chain rule. So this f ball g is the composite function. So function f with function g as a parameter, and then g has a parameter x. So we could write it a different way with the d notation of df gx dx, or then we could use the dxf gx. But the end result is that we're always using the dash notation. So what it should reduce to, and what is the chain rule definition, is that we take the derivative of f, have the non-differentiated, the original form of g as a parameter, and then multiply that with the derivative of g. And if someone's reading MAL, which is the Finnish high school tables, now I forgot the actual word I should use for those. So yes, that reference has a g-fx and f-x, but that doesn't matter. We've just swapped two symbols. What the symbol is, it doesn't matter. We could have a banana function and an apple function and make a I don't know, a smoothie or something. So the symbols exactly don't matter. Usually we use Latin letters. On some cases we start using Greek letters, and in case of infinities, we typically use Hebrew. I can recognize Aleph, which is also the emblem of the student union. So that's certain types of infinities are Aleph groups. And now I can't remember what the topic was, but on some type of algebras, you might, if you ever run into those, you will find that some symbols are using Cyrillic letters as well. So it was a research topic mostly done in Russia, so they use Cyrillic. And then we run into something called the Leibniz notation. So we're now defining dy dx. So what we want to find the change of is the y variable. So y is f ball gx when x changes, and now we're adding this kind of a helping variable there. So we end up having adding du over du and dividing so that we get two operations, dy over du and du over dx. And that's the Leibniz notation for the chain rule. So we're doing an intermediate step. Of course, it could be possible that we just calculate what the composite function is and then differentiate that. But occasionally, for example, the example or the warm-up questions, we already have to have some of the functions differentiated, so no use of doing extra work. We can use the work we already did. That's one of the key ideas of using a function, is that if you already have the results, don't really do it, use the already computed values. So example, we're need to find the differential of y equals square root of x squared plus 1. How would you do it? Well, the same thing we had a glance at last time. So divide first into elementary functions, and because we do not have an elementary differential of the square root of some function in it, we'll need to use a chain rule. So our outer function, the f, we call now the outer function is square root of u, and then the inner function is x squared plus 1. And then we calculate those. Shouldn't be too hard. So that's u to the power of half. That's the f. Let's have a look on the board just together anyway. Here's something you probably have done. And why I should probably pin myself. People on the Zoom call, do tell if you cannot see this. This looks a bit fuzzy on my screen. So we had y equals x squared plus 1, and we divide this into two functions. So if u equals square root of u, now we immediately know that u must be positive, but it turns out this is always positive, so that's not a problem with the domain, and that's u to the power of 1/2. So f dash u is okay, elementary powers, so that's minus that. So that goes on the front, and minus 1, so the power of minus half, which is, if we convert back, it's well, actually, let's do it this way: 1/2 times u, and then we had the gx, which is x squared plus 1, which we could divide into two parts, but derivative of 1 ends up being 0, so it is a bit superfluous. So the derivative of x squared is 2x. And then the chain rule was that when we have fgx, that's f dash gx g dash x. So, okay, we grabbed f dash, which is half times 1 over a square root of what now gx goes there as it is. Actually, this is wrong. So g dash x, of course. I was jumping a step. With two easy calculations, you need to be careful. So this is just x squared plus 1 here. So that was the argument or parameter there, and then g dash x. So that's the 2x there. And these cancel out. So we end up having argument is x over square root of x squared plus 1. So that was a really simple example, should be easy to follow, but in mock we hopefully end up seeing slightly more complex things as well. Yeah, do ask.
What did they use for in the Leibniz notation?
Yeah, we didn't actually use that, but we could have also done that, and we'll end up needing that when we start doing implicit differentiation a bit later. So then it gets a bit more useful. So it kind of just a short intro on the Leibniz notation. There are preferences, so these are kind of equivalent between each other, whatever notation you use. But yeah, the implicit differentiation makes more sense if you use a Leibniz one.
I still don't understand what the U was in this. Is it just the
yeah, this kind of just stands for the parameter, and the parameter here is the entire utter function. So we are just replacing that with something else, so we can take our minds off of having the utter function here. So we could have.
So the du is actually the divided.
Yeah.
Okay.
So we could have put in here also g, but this gets confusing because formally this means now that the entire g function is put in there. So we are, for the purpose of kind of underlying that we're just assuming that there's some variable, and we're using a different variable there. And did we get the same result? We did. This gets occasionally annoying. Last year I completely looked up on one of these examples because I hadn't really differentiated that much by hand in something like a decade. I end up doing it numerically. So if we use these kind of things, we end up having new rules. So essentially here u could be some kind of a function. And so now if we take this differential of the inverse of a function, we should get minus the inverse square of the function times the derivative of the function. Same with if we have a square root of a function, we should get essentially what we got here, half of the inverse square root times the derivative of the function. And then general power, if we take the derivative of some power of a function, we do have that rule. So power of the function times the function to the power minus 1 times the derivative of the function. And now if these of course hold if we have just a variable, but if we have a single variable, then of course just plain what's the derivative of x? Well, that's a constant 1. So then that du dx part disappears if you're doing this just with variables and not u as a function. And absolute value rule. This SGN is the signum function. So what's the sign of that? So we end up having or you could replace it with the u over absolute value of u. We end up having a partially defined function there. Okay, so let's practice. Does everyone have pen and paper, or at least something to do math with? So what do we get with 2x plus 3 to the power 6? Have a look on these for 5 minutes, or if you have a computer there, you can also have a look on these, and I can put the previous slide if you want to.
Do you want us to solve these?
Yes.
Okay.
So just a little bit of practice. So the typical quip is that a lecture is an event where stuff goes from the lecturer's notes via spoken speech to the student's notes without passing a brain. So we want to avoid that. Yeah. Yeah. So that's the absolute value you can define as u over absolute value of u, or you can check where the function changes signs. This is relatively easy for the function we have here. I think it was 1 minus x squared, so it changes signs at plus minus 1. Yeah, it was 1 minus x, so when x is plus 1 or minus 1, it goes to 0. And now I've also swapped around the variables a bit, so even when the variable names to change, it doesn't really change how you do the mathematics. Of course, unless you have a defined variable, we'll run into that later, then you're going to have a spot where then the rest of the variables are constants. Just not constants that are expressed with a number, but constants that are expressed by some other symbol, which the value of which we might not know at that point, but we can still use them in computations. And it's up to preference whether you just rather cite the rule and substitute the paths you've identified, or if you go via the chain rule. But the main thing, show your work so you don't go from the initial equation and then just the answer, because that's not what we're supposed to practice here. It's a bit simplistic, but I think these are more or less straight from the textbook. I didn't check, but considering the hurry I was doing slides last year, it's quite likely. Or then I'll just pull them out somewhere. And this is the reason why we don't want to use, we usually want to use a different symbol here as well, because this can get confusing if we're having similar functions. Okay, I can't remember from memory what this was. It's negative powers of negative powers. Should be something like minus 11, no, minus 10 plus 2 minus 11. This is an incredible platform to do direct calculations in the head, because there's absolutely no way of knowing how I arrived at this conclusion. And then we have 3 times 10 to the power minus 1. So 3 goes in front, and times minus 1 times something like that. Then we have minus minus, so it's 30 plus. This is supposed to be t here. Did these ones go right? I've been known to make errors. That's why usually when I have time, I usually always, if it's feasible in that kind of problem I'm solving, I try to substitute the solution back to the originals and see if those still are valid, just to check, something like that. I skipped the internal steps here, so if I had done this properly, then this 2 plus 3 over t should be okay. 2 is a separate function, but that's goes to 0. Okay, then 3 times t to minus 1. Okay, 3 we can take before the differentiation sign. So if we do t 3 t minus 1, if we really want to go to elementary functions, then this is the same as number 3 goes before differentiation and we get t to the power of -1. And now this is the elementary differential here. And did someone get sine one? So this is probably partially defined. So y dash. So that y dash is when -1 is x to 1, that's something, and then I cannot write English anymore. Otherwise, so something like that. So we had that kind of a solutions. I'm not sure if anyone online had a peek at the screen share.
The second one, the 30 becomes positive, right?
Yeah, because we're having a -1 from this t to the power of -1, and we had -10 from the original power -10. So
Okay, because I wasn't sure if that was a negative or an equal sign. Okay.
yeah, that's an equal sign here. Yeah.
Is the one below the 31, is it the same question or is it the next one?
This is the same question essentially. So going what this inner function derivative is, just going by part by part. So that's where we end up. If we really went back to the elementary derivatives, then we do have t to the power of -1 times 3, and then start substituting back. So, okay, so you should go essentially by this detail that I'm showing here. I now jumped slightly here, and based on questions, it's already slightly more difficult to follow when I've skipped steps. And that's the same thing for me when I'm grading. If I want to see what you're doing, then kindly don't skip steps. I have possibly no idea at some points what you're doing, especially if you end up doing notation errors. And like Halima noted, it would be really easy to write the equal sign a bit too quickly, and then suddenly I have an extra minus there, which I just didn't notice, and end up using in my next result. So and otherwise simple. So we have just the regular derivative of that when we're positive. So within the unit distance on plus and minus. So that's minus 2x. And otherwise, we need to flip it around. We get plus 2x. Okay. Anyone need a break? We've been going through for 45 minutes now. Nope. Okay, then let's go on. Okay, we still had this one, but technically you could go to general fractions as well, going fractions by fractions, but that's a bit silly example. Let's skip that for now. Because you can do that, you could do that with just the regular powers. It's just the extra power of 0.25. Okay, the trigonometric functions. Okay, so sine and cosine functions are continuous for all. Of course, in some cases, we may want to limit ourselves to look only one cycle. And then the limits, totally continuous, and the limits are the same on both sides for theta goes to 0 for sine. And then cosine where theta goes to 0, that's 1. So those are essentially the limits of those functions themselves are the function values. Then with the tangent function, you're getting funny stuff. But there, when you limit yourself working just on one cycle, then that doesn't harm too much as long as you're careful with the domains. And then there's one interesting result. Sine theta over theta when theta goes to 0 is 1. So it goes to 0 over 0. Let's have a look. This also shows one example how to use a squeeze theorem, which in general, at least for me on the first glance, looks like we just wave our hands and stuff happens. So let's consider a unit circle again. And now we're going to manipulate the equations of the areas that end up being found in the unit circle in such a way that we can show that one of the areas with a certain multiple ends up being sine theta over theta, and by comparison to other areas, one of which is always smaller than the reference and one is always larger than the reference, those smaller or larger ones end up being 1 when we go to 0. So therefore, by the squeeze theorem, the limit of that ratio must always also be 1. So we actually don't need the full unit circle. We can do this on the first quartile. So we call the first quartile the part where both x and y axes are positive. I'm going to drop the screen share for a moment. But for the benefit of people over here, let's keep that on the screen. So what we're actually doing is, well, this is supposed to be the quarter of the unit circle, and not too bad. And we're having angle theta here. This is 1. And now the height of this point is, by definition, that's sine theta. So if we draw here a straight line, origin is here, let's call this A, let's call this B, then the area of the triangle OAB is, well, okay, the height times base divided by 2, base is 1, so it's sin theta by 2. The sector here, so if we consider the area of the, well, this is formally meaning angle, but let's now pretend it means the sector OAB. Okay, the sector area is, when we're talking radians, it's r squared times theta divided by 2, but the radius r is 1, so it is just theta over 2. And then this triangle, let's call this point C here. Then the area of that triangle, well, the height here is tangent of theta, which is a ratio of sin theta over cos theta. So we end up having area of the triangular OAC being sin theta over 2 cos theta. So I don't like drawing on the computer. I should do more of that, but I'm really slow at that, so that's why I prefer to show that on the board. Let's resume regular programming now. So when we know that the inside part is smaller than the inside triangle is smaller than the sector, which is smaller than the outside triangle, we get this sine theta over 2 is smaller than theta over 2 is smaller than sine theta over 2 cos theta. And now we're going to multiply all sides by 2 over sin theta. If we are on the first quarter or the first 2 quarters at most, well, we're now only on the first quarter, so that's good enough. Well, sine is positive, so we do not end in negative ones. Why was this important? We don't go negative when we're multiplying inequalities. If an inequality is multiplied by a negative factor, then we need to remember to swap the signs around. So I'm not actually completely sure what's the official formal term of that. So I brought in here that no inequalities flip, but actually in this case it doesn't really matter, because after multiplying sine theta over 2 by 2 over sine theta, we get 1. Then on the middle, we get theta over sine theta. And then on the right side, we get 1 over cosine theta. Well, when theta goes to 0, cosine theta goes to 1. So it's 1 over 1. And theta over sine theta and 1. Okay, we're looking for the inverse of that, but the inverse of 1 is 1 as well. So we get that on the both sides we get 1s, and the middle we get something that's essentially the same as sine theta over theta. And therefore, by the squeeze theorem, the limit of that when theta goes to 0 must also be 1. Okay, derivative functions. Derivative of trigonometric functions. So we could use similar limits to arrive to these derivatives, but these are something you should mostly memorize. So these are most important ones. So the derivative of sine is cosine. Derivative of cosine is minus sine. Tangent has a few options. So 1 over cosine squared plus x is 1 plus tangent square x. And then, well, cotangent is situationally useful. And of course, things like sine squared x plus cosine squared x equaling 1 are also useful. So occasionally you need to manipulate the formulas to really arrive to those parts. So this is again chain rule here, essentially on y equals 3 cosine x, y equals pi tangent x, and this y equals form is essentially the same as using the fx equals. So, but now with fx we have defined what's the variable, so we do know that. So cosine s minus rx. So in this the third equation, what's s? Is it a variable? Who says it's a variable? Raise your hand. No one? Okay, so who says it's a constant? Raise your hand. Oh, okay, now we're inventing new maths because it's not anything apparently. Well, it could be a function, but then we don't know. No, it's a constant, so it could be any number, and you can treat it as it was a constant number. Similar to r here, when we have defined that it's a function of x, then we know that the r here is a constant, and we can just treat it as if it was a number. And the last one, if I remember right, well, we can do it with the regular chain rule, but it could also be. I was thinking about some conversions, but it doesn't really matter that much. So on the first example, what's the inner function? So if you divide that by chain rule, what's the inner function in y equals cosine 3x? Any ideas? At this point, I'd usually start asking if you could tell me any number, and then start going 1, 2, 3, 4, 5, and u. 3x, okay? Yeah. So then the other function, what's left? So we have cosine u, and we have u equals 3x, and differentiating. So f dash, I'm using shorthand here by dropping off the, well, actually this was a y. Well, let's write that way. So I'm using shorthand by dropping off the parameter. So that was a minus sign. U dash is well, that's us 3. So we now get that y dash, which was the complete one, is outer function minus sine inner function 3x times the derivative of the inner function times 3. In the old school way of using handbooks, now I remember the word, so I'll give you, so those tables, we would probably just look more, on more complex case, we would just look to readily differentiate formula, so that's one of those. Well, the tangent is quite similar. We actually have the formula there for that. That's the external here, and then the internal. And now we're getting this 1 plus as a result. So for the tangent part, we're having outer function is tan u, and derivative of that is 1 plus tan squared u. Inner function is just pi x. It was x, yeah. So we get the derivative of pi. And now when we put it together, 1 plus tan squared inner function here. So pi x still there. And times pi. So it goes on front. So if you want to clean it up a little bit, it ends up being pi plus pi 10 squared pi x. The next one is essentially similar. We're having different inner function. S is just a constant, so the constant goes away. Then we have minus r. Well, essentially, if you replace the inner function in the first example, and then the 3 on front goes to being multiple of minus r, that's it. And the y similarly, so now we're getting inner and outer functions. Need to remember to keep the entire function there when we're having what kind of changes. I think this shouldn't go on that much longer, so a little break might have been useful. Yeah, okay, we'll still need to have a look at the exercises. So Arthur's functions, so these are inverse functions. Now, I'm not sure if we went through the concept of the inner function, but certain types of functions do have inverses. If we're having a monotonically increasing function, that's why it was in the beginning of the notes. So something that for every point of fx, then fx is smaller than fx plus some small delta, where delta is a really small difference. So this means it is monotonously increasing. And now, if we state that y is fx, such of a function that fulfills that x is y, f with a parameter y, so do note just this -1. That is the inverse function of f. And in the case of trigonometric functions, these Arcus functions are the inverses of sine, cosine, tangent.
Is that not sine?
Yeah, that's not sine. It should be cotangent. Yeah. So lowest, and this is not. I need to edit not the original PowerPoint slide, but yeah, that's a cotangent. Yeah.
CTJ.
Yeah. So the final one is the derivative of COT x is minus 1 over 1 minus x squared. Okay, brownie points, no one catch that last year. So if you consider what those are, then sine, and we have cosine, and then these two have similar relations of tangent and cotangent. And this is essentially how you, but let's have a look at the exercises. So really simple things this time. Ask. And yeah, there's a homework returning tool. Kindly use your student number as an identifier. It is possible that we do have 2 students with the same name, but we don't have 2 students with the same student number. And just to make it slightly easier to grade, I'm still going to read them all, but exercise 01 tells it's exercise 1, problem number, and then what number of problems you solve. So if you solve problem 1 and 3, you can submit to initial string and then p13.pdf. Yeah, and yes, I'm wanting these as PDFs. So if you have those as photographs, you can either print those photographs as PDFs, or you could, for example, put them in the Word and then save as PDF, whichever way suits you better. Kindly try to keep them in order so that you don't have, for example, 132 order of homework problems. And we're gonna chiefly go through these onto exercises. So we'll go through these little by little. So we're having 3 functions. First, differentiate the functions themselves. These are warm-up. You don't need to return these warm-up problems. And then let's see basic application of the multiplication rule, the division of functions, and then this chain rule. Similar things, if we have these 2 vectors, what are the magnitudes? What's the vector v subtracted from vector u? What's the angle? Well, actually, if you're smart, you're gonna do first one of these. So probably the dot product first, and then by the definition of dot product and knowing the magnitudes, you can easily calculate the angle and then the cross product. So we'll have a look on the exercises. I can actually, if you want to, I can try to get the solution of these done as a reference. And then we can additionally have a look at the exercises if you have any questions on those basic things. But that's something that you should be mostly familiar with from high school. Then problem 1. Usually this in our university has been that how fast can you cool a glass of beer? But I took the numbers from a web example, and it is essentially nearly boiling water that's being cooled down towards the ambient temperature of 26 degrees. So someone's having really hot rooms, and then find out the equation that tells how this changes, and find out when the change is relatively low, and then at what temperature is the liquid at that point. It should be just water. And this does have some applications. For example, in making of steel, the control of the cooling rate is important, so we know what kind of a crystal structure. That was the right way to say it, I think, crystal. So it goes to. And from the equation, we can already say that probably the ambient temperature is a factor, and then there's, how many of you do remember what is Newton's cooling law? Okay, so the difference in temperature is a factor, and then there's some factor K, which we call the cooling factor. But we'll talk about those later. It's going to be one example of differential equations. So a simple differential equation is fitting to a cooling factor. Problem 2, we have, oh, I forgot to go to lab and pick up a tool. Well, I can show you a tool tomorrow or have some images. So we're going to have a cutting tool. And that cutting tool does have force sensors. So, but the tool is not straight. It's not a pushing tool. It's a cutting tool. So in order to figure out what kind of forces actually act on the tool surface, then we'll need to do a little bit of rotation. And one way we can do this is that we project those project those. Well, first we will probably want to calculate the resultant force, and then we project that to the tool surface. Or alternatively, project that normal to tool surface. Then the rest of the forces. So what's the orthogonal component, and what's the tangential, and what's the normal component? Those are essentially forming a right triangle. So it should be middle school or even primary school stuff to calculate what the other component is. And yeah, we're having only 2 axes, so it's 2D. And then the third problem, well, that's relatively simple. You can actually, if you want to, you should be able to reduce that to basic trigonometry, but you can also do this with vectors. Now we're multiplying a vector with a variable, but it's still like a scalar variable at this time, so it should not cause you much trouble. So relatively simple still, and just testing on if you can figure out what the components are. So in a mathematical representation of these problems, and then the solution should be quite straightforward. I want to, for these 1, 2, 3 problems, these are the ones you should return, and then will be help available on exercise, but I won't show you the solutions until after the deadlines go. You can work with each other. Still, these are quite pretty simple, but if you want to discuss these by yourselves, go ahead and discuss. So that's essentially the intended part, that you do occasionally discuss maths outside of class as well. All right. Any questions at this point? I'm not sure if this is going to be a trend. So if someone wants to keep statistics, but does it happen so that our Tuesday lecture is always short? Wait, last week, Tuesday lecture was long and the Wednesday was short. So maybe we're doing an inverse this week. Let's see. But that we're going to see tomorrow. Okay, any questions? Yeah. Anyone hungry? Okay, let's go eat. All right, and recording.